So now recall that in a scalar manifold locally we can write the metric as del alpha del beta bar k. Okay, where k is some function. Okay, it's not globally defined, so on the overlap on of two coordinate touches, k need not be the same. Now, given a g alpha beta bar like this, we can construct a 1-1 form. 1-1 form. J, which is g alpha beta bar, dz alpha, which dz beta bar. Now, note that this wouldn't be possible in a real manifold. Okay? In a real manifold, G mu is Gmn is symmetric, right? Whereas forms are supposed to be antisymmetric. Okay? So, in a real manifold, it will not make sense to construct a form out of a metric. But in a complex manifold, it does make sense because the z's and z bars are treated differently. Okay? The antisymmetrization is in the z's and independently in the z bars. Okay? But not, it doesn't make sense to antisymmetrize in alpha and beta bar. So these are different kinds of indices. Okay, so this is the one form. But there is something more, which is that del bar of J is closed, is 0. Why? Because del bar of G, you take one more derivative, del gamma bar. Okay, so this is del gamma bar, G alpha beta bar. dz alpha equal dz gamma bar equal dz beta bar. Okay, with a minus sign because we will take the del bar through the dz alpha. And this is 0. Okay, this is 0 because you have to antisymmetrize in gamma and beta bar. Gamma bar and beta bar. Okay, and you already have a del beta bar, del z beta bar here. So this is 0. Okay, which basically means that J must be an element of H11. Okay, because J is a del bar closed form. In fact, del J is also 0. Okay, and we can also show that J is harmonic. This is a harmonic representative. So in any case, so what we see is that J is an element of H11. Okay, and this is what is called a Kähler class. So on a Kähler manifold, we can define a Kähler class which is a particular element of H11. Is this clear?
You said for real manifolds one cannot do this, but sometimes we also use this symplectic constructions on real manifold where we have an antisymmetry.
Yes, you need some additional structure. Okay. Here, so if you didn't have any additional structure, then from metric you cannot go to forms. Right? Here you use a complex structure to do this. That way, complex manifolds are also real manifolds. Right? But the reason that we can do this is because of this additional structure. Okay. So this is true that given a Kähler manifold, we can identify an element of H11 which is called the Kähler class. Okay. But it also goes the opposite way. Okay. That now you have to know that in the same complex manifold, okay, can we change the Kähler structure? Okay. Can we pick a different Kähler metric? Okay. And what one can show is that given any element of H11, okay, we can use it to define a Kähler metric. Okay, because an element of H11 locally has this structure. Okay, and then you can use that to construct a Kähler metric by using this. Okay. So, conversely, elements H11 give positive error metric. So this gives you a way to count the dimension of the killer moduli space. Namely, the dimension complex the dimension of the killer moduli space is simply H11. Okay. So this means the dimension of killer moduli space is H11. Because given an element of H11, we can use it to construct a scalar metric. Okay, because given an element of H11, it defines something like J, okay, which has the index alpha beta bar. Okay, and now you simply take that index G alpha beta bar to define a metric rather than a form. So later on we will try to get a similar relation involving the complex structure moduli space. Okay, but for now let's proceed with this.
Given this G alpha betas one can construct, only one is going to be the metric of the manifold, rest are not, right? I mean,
that's it, yeah. But the point is, if you choose the rest, right, then we can construct a different metric on the manifold from the other elements.
so it's converse, one cannot uniquely fix which one is the metric. I mean, any one of them could have been the metric of the manifold.
Exactly. So given H11, of course you cannot fix the metric uniquely. But given an element of H11,
Each could define
each defines a metric, scalar metric.
Each could have defined a new
Scalar metric, exactly. Right? So given H11, of course the metric is not fixed because you can put a family of metrics, right? And that family is parameterized by H11 parameters. Right? Because the H11 levels the dimension of the space of this. Is this okay?
But all these possible metrics,
Yes.
is it guaranteed that from a given metric I can continuously defer to get to?
Well, here it is by definition because H11 is a vector space, right?
Yes.
So any element is continuously deformable to any other in the vector space.
So the metrics are also
Exactly.
And this tells us anything about the topology of the killer moduli space?
No, this is a local construction. Right? There may be global identifications, which of course this doesn't know about. Right? That's yeah. Okay. Now there is an important result which is conjectured by Calabi and proved by Yao. Yeah, that's what gives the name to Calabi manifold, which says the following. Okay, I think before I say what it says, I have to do a little more, introduce a little more, few more things. So given a scalar metric like this, one can introduce a Ricci tensor, okay, which also has only alpha beta bar component. So Ricci tensor has alpha beta bar component. And in fact one can show that this object alpha beta bar dz alpha d z beta bar is a del bar closed 114. which means del gamma bar or alpha beta bar is antisymmetric, or the antisymmetric part is 0. Okay, so which also locally means locally that R alpha beta bar must be having the form del alpha del bar beta or something. Okay, so this, because this is del bar closed, this also defines an element of H11. Okay. So this defines an element of H11, and this is called the first chart class. Okay.
R alpha beta bar is the first chunk.
This element of H11 is the first chunk class. Okay. So in element, when you talk about the element of H11, right, it's 1 forms up to equivalence, right? So the whole equivalence class, okay, is called the first chunk class. Is this okay?
And this construction is given the metric, right?
Given the metric, yes.
So we
Exactly.
need the metric for it.
Exactly. Suppose you are given the metric, right? But this property turns out to be topological, that under continuous information of the metric, the first chunk class will not change, but I'll come back to that.
So for all Kera metrics, which tensor is Denver closed?
Yes, I think for all Keller metrics, Ricci tensor is Del bar closed, exactly. Okay, now for a Calabi-Yau manifold, okay, we know that we have been saying that it's Ricci flat. The Ricci flatness is in fact a very important property that you want because it solves Einstein's equation. Okay. So it's clear that if we put a Ricci flat metric, then the first chunk class is 0. Okay, it is identically 0, right? The R alpha beta bar is identically 0. Okay. So for a Calabi-Yau manifold, so the first chunk class vanishes. Well, I should say for a Calabi-Yau manifold with Ricci flat metric.
Why is that? You need to say it additionally.
Because Calabi-Yau manifold is a topological property, right? It doesn't, but Calabi-Yau manifold by definition doesn't know anything about the metric, right? It's a topological property of the manifold. Okay? But if you put a Ricci flat metric, then this is 0, right? And Ricci flatness, as I have been saying, is important for us because after all, our interest is in finding solutions to Einstein's equations, right? So Ricci flatness is an important property that you want to have. Right? There is something else that will be coming to later, that is supersymmetry, but certainly you have to have Ricci flatness, okay, because you are trying to solve Einstein's equation. Okay, now this theorem tells us that given a complex manifold, complex scalar manifold, which means that suppose you have a complex manifold and also the scalar class of the metric is given. Okay, but in a given scalar class, of course, the metric choice can vary. Okay, because scalar class only specifies the H11, okay, the element of H11. Okay, but the element of H11 still leaves you with the freedom of adding exact forms. Okay, so it can vary. So given a complex scalar manifold, which means given complex structure and scalar structure, given complex structure and scalar class, further satisfies that its Chern class vanishes So let me repeat again. Okay. Imagine that you are given a complex manifold, okay, which is also scalar, okay, which means it admits matrix of the scalar type. Now you fix the complex structure, okay, which may have its own moduli. It could vary. For given a real manifold, you could vary the complex structure. You fix the complex structure, okay, and you fix the scalar class. Okay, that means you pick an element of H11, okay, but that doesn't fix the metric completely, because given an element of H11, of course there are many representatives. Okay, you pick any one of them, okay, and suppose you find that when you calculate the Ricci tensor, when you calculate the first Chern class from there, okay, it gives a vanishing element of H11, which means that it's del bar closed,
So
del bar exact.
here by
Yes.
scalar class, we mean I just choose any equivalence class from H11 and interpret it as scalar.
Exactly, that's right. Okay, so what they showed is that given this scalar class, okay, given a metric, okay, in this scalar class, that there is a unique Ricci-Flach metric that you can find. Okay, and this unique Ricci-Flach metric. So, see, the reverse is true. If the metric is Ricci-Flach, obviously the scalar class vanishes, right? But having vanishing scalar class, having vanishing first Chern class, if the metric is Ricci-Flach, the first Chern class vanishes, because first Chern class is the H11, the element of H11 that is represented by this. So obviously, if R alpha beta bar is 0, this is identically 0. Right? So it represents 0 element of H11. But what this is saying is the reverse. Okay? That having a 0 element of H11 is a topological property. Okay? Having a 0 element of H11 doesn't mean that R alpha beta bar is 0. Right? It only means that it's del bar exact. Okay? But statement claim is, okay, and as I said, it has been proven, okay, that given this in the same scalar class, you can choose another metric, okay, which is a in fact unique metric, which has R alpha beta bar identically 0. Is this point clear?
Non-triviality is being able to define such a metric global.
It's a differential equation, right?
Mm-hmm.
Okay, and what you are asking is, does it have a solution that exists globally? Right? That you have to find a metric which satisfies the differential equation.
Locally, this statement is then not locally one can.
Locally you can do this, yes. Right? Globally, if you want to try to solve, see, even locally, you start with a metric which is R alpha beta bar not 0, right? Then you have to deform it to make R alpha beta bar equal to 0. So locally also it's a non-trivial statement, but it's easier to prove locally. Okay? But the important part is that globally also it's true. It's a differential equation, right? And what I am asking is that does a differential equation have a solution? Okay? Not all differential equations have solution, right? If I have two differential equations in two variables, if del x of a function is given and if del y of a function is given, okay, it doesn't always have solution. There is an integrability condition. And that of course has to be satisfied. Okay. But then, so there is a local integrability condition. Right? But on top of that, there is a global integrability condition. Okay. And the claim is that both of these conditions are satisfied and you can actually find a global solution to these differential equations if the first Chern class is 0. Is this point clear? Okay. The reason that this is important, okay, is that nobody has so far constructed a Calabi-Yau manifold with Ricci flat metric. Okay, it's a very hard problem, and that there is no single example except for tori. Okay. There is no single example known where the metric has been explicitly constructed. Okay. However, because of this theorem, okay, we know that if we can find a manifold with vanishing first Chern class, okay, then it will admit a metric of a Ricci flat metric, okay, and hence it will do the job that we want it to do, even though we may not be able to explicitly construct the metric. And as we will see, a lot of the analysis can be done without knowing the metric explicitly, okay, but just from the topology. Okay, but the existence of a metric is important. Okay. If such a metric didn't exist, then of course you cannot use those manifolds. Yes.
Does the vanishing first Chern class imply that the vector bundle is trivial?
Well, it doesn't mean the whole manifold is trivial. Right? That particular vector bundle which defines the first Chern class.
Independent sections.
Exactly. So the particular vector bundle that is responsible for defining the first Chern class, that is trivial. Yes.
So here is what is the relevant bundle? Tangent bundle.
That's right. Yeah. It's a tangent bundle. Locally, basically, okay, it's holomorphic tangent bundle. It's basically what it's saying that the U1 part of the connection can be made 0. Right? Because there is He flatness. If you think of the SUN holonomy, right? What was that condition? That the U1 part of the connection should vanish. Right? So that's the statement. That bundle can be made trivial. SU3 part is still non-zero in general. Okay, is this okay? Yes.
The manifold being Calabi-Yau is it comes with this condition that it has to be Ricci flat or first
No.
Chern class.
So now the first Chern class vanishing is the condition.
First Chern class vanishing.
Exactly. Okay. And as we'll discuss some examples, okay, that is much easier to implement than having to construct the metric explicitly and checking that you have a Ricci flat metric. Okay. That's a very hard problem, and so far there is no explicit solution in any case except for tori.
First Chern class is a topological statement.
Yes, exactly. First Chern class is a
So
topological.
without knowing the metric or
We can check whether the first Chern class is 0 or
whether
not.
it is Ricci flat or not.
Yes.
Just knowing that one topological property, this first Chern class is vanishing,
Exactly.
one can decide that it's a Calabi-Yau.
That's right. Okay. So I'll not give the most general discussion of how to construct such manifolds, but let me just give one class of examples. So these class of examples are constructed by starting with CPN, okay, and then constructing polynomials in CPN to get subspaces of CPN. So CPN basically is described by a set of n plus 1 complex coordinates with the identification that this is the same as lambda times z1 up to lambda times zn plus 1, where this is a complex number not equal to 0. So lambda belongs to C star, which basically means it's a complex number not equal to 0. And you exclude from this the origin. Okay. So when we say that it's the space of the spanned by the z's, okay, it's a space spanned by the z's, but not the point, excluding the point where all the z's are 0. Okay, so this is CPN. Okay, it's a compact space.
Like real projective planes can be thought of as like a set of all the straight lines passing through origin,
Yes.
excluding the origin.
Extrude the origin. So this is like complex lines.
Oh, lambda is the translation on that line.
Exactly. Lambda is the multiplication here, right, by some arbitrary complex number. So identify points which are related by overall scaling. Okay, now suppose you want to construct a set of equations, okay, to form a subspace. Okay. So if you use these homogeneous coordinates, okay, then an equation like P of z equal to 0 P of z, let's call it P of z1 to zn plus 1 equal to 0. This makes sense only if this is a homogeneous polynomial, right? Because otherwise, if you have a one representative z1 to zn plus 1 and another representative which is lambda times this, right, they will describe different conditions. But if it's homogeneous, then of course under this scaling you get an overall factor which doesn't matter, okay, because you are setting this equal to 0. So this has to be homogeneous of certain thing, homogeneous of degree city. Okay. And in general, we can construct a set of homogeneous polynomials of this form. Equal to 0. So this is, suppose this is of degree pi, this is degree bi, and I can run from 1 to k. Now this is clearly a complex manifold. Okay, its complex coordinates are induced from the complex coordinates of CPN, okay, and these are also of course preserving the complex structure. These are holomorphic functions, right? Holomorphic coordinates only. So this is clearly a complex manifold. What is the dimension? So the dimension of this manifold is n. Okay, this is the n of CPN. Okay, one you start with n plus 1 coordinates, but because of the scaling one coordinate went away. So n is a complex dimension of CPN, and then you have to subtract from here k, because you are getting k equations. Okay. So n minus k complex dimension. Now it turns out that CPN is a Kähler manifold. And the Kähler structure of CPN also induces a Kähler structure on this submanifold. Okay, so this is also a Kähler manifold. Okay, which you can get, which basically descends down from the Kähler structure of CPN. Kähler form of CPN.
This is something obvious, it's a non-trivial statement.
What? The CPN is Kähler?
No, that descends down to this.
Well, basically you take the, suppose J is the suppose J is the Kähler form of CPN. Okay. So you can basically pull back, because these are just subspaces, right?
Yes.
Some differential equations, so you can pull back J on these subspaces, right? And then you have to make sure that it's Del bar closed, right? Which you can say explicitly, because these are holomorphic equations that are restricting. If to begin with J is Del bar closed, right, then once you pull it back, it also remains Del bar closed.
The topology of this manifold will not.
No, we are saying the Kähler structure, right? So you have to make sure that it admits a Kähler form,
Yes.
right? So what I'm saying is, you take the Kähler manifold, Kähler form of CPN,
Yeah.
right, and just pull it back. So it's a 1-1 form, right?
Yes.
So pull it back on the submanifold, and it remains a 1-1 form because it's holomorphic projection. And you have to make sure that it's Del bar closed. It's a differential equation. equation, right? That's what topology involved here.
No,
They-
whether that thing has global solutions or not, their topology.
No, J already exists,
Yeah, it already.
Right.
But that's in whole CPN.
exactly. So it's pullback. So if it exists in whole CPN, right, it also exists on its pullback. See, if you have think of a metric on a space. If you take a submanifold of a given space, the metric automatically induces the metric on a submanifold, right?
Yeah, that's true.
Okay. So it's the generalization of that. If there is a 1-1 form to begin with on the whole space, right?
One form will be descend down. That is okay, but I'm worried about the conditions.
What condition? It is differential condition.
Dilbert close. That will be-
Dilbert close. So the point is that, so what I'm saying is, as long as it's Dilbert close in the original manifold, right? You can check by this pullback condition that it's also Dilbert close, remains Dilbert close on the submanifold. Yes.
For, because it's a killer class, it should be del bar close as well as del closed, right?
Yes. But I mean, usually HPQ is defined by Dilbert close, but yes, it is true that it will also be Del closed, exactly.
So, is the other condition satisfied automatically? Like if we just check del bar close, then is it automatic? Do we-
Well, it's not automatic in the sense that you can always choose a representative, which is not Del closed, right? If you take the harmonic representative, then of course it's both Del closed and Dilbert closed. Right? But if you just demand Dilbert closed, it may not be Del closed because you may choose a wrong representative.
Fine.
See, what you can do is you can take the Kähler form of CPN, right? The Kähler potential K, and restrict it to this on the subspace, right? And then del del one on the subs of that K will be the pullback of that Kähler class. Okay, so this is scalar. The question is, what is this Chant class? Okay. There is a general formula which I will only write down, I will not prove. Okay. So to calculate the first Chant class, what you have to do, okay, basically that is, so the Chant class of CPN is 1 plus j to the power n plus 1. So the first Chant class, I will explain what you have to calculate to the first Chant class. So I equal to 1 to k. This is just a formal product, 1 plus j, 1 plus dij. Okay. So take this expression, okay, this is from CPN, these are the constants, and just expand it out formally as a power series in j. Okay. So the first coefficient of j is the first Chant class. Okay. So this is j times n plus 1 minus sum over di. And then there are other terms which contain information about the higher Chant classes, which I will not worry about right now. Okay. So this object is the Chant class of this manifold, of the subspace. So which means that as long as this coefficient vanishes, we are guaranteed that this subspace that we have constructed has vanished in first Chant class.
Could you repeat the left hand side is what?
This one, left hand side.
Yeah.
Oh, this was the basically the what would be the Chant class of CPN, and these are, we are dividing by this because we are putting the constants. Okay, so that's the rule that if you take, so this is what is called complete intersection in CPN. You take multiple constants, right? Each describes a subspace, and what we are calculating is the intersection, and this is a formula that allows you to calculate a Chant class of that intersection. Okay. In particular, if you didn't have anything in the denominator, then the Chant class would be j times n plus 1. Okay. So what this says is that as long as you choose
What is J? Sorry.
j is the Chant class of CPN, okay, and in this context it's the pullback of that on the submanifold. Okay, so the j was describing a 1-1 form. Okay, you just pull back that 1-1 form on this. Okay,
But what do you mean by the polynomial of one more?
Yeah, so polynomial you have to think in terms of wedge product.
I see.
Hard coefficients correspond to higher churn classes, but for our purpose it's only the linear term that's important. Right? So just formally expand it out, okay, and pick the linear term, that coefficient gives that. So this one gives a churn class of this intersection, this manifold. Is this okay?
What will other terms give, sir?
They will give the higher churn classes. Okay, and of course, I mean, if the manifold has, like if it's n complex dimensional, right, then this expansion may go on forever. Right? But you have to stop at n because if you take 1-1 forms, right, the n-fold wedge product, beyond that everything vanishes. Okay, so we need n plus 1 minus sum over I equal to 1 to k di equal to 0. Okay. And if this condition is satisfied, okay, then you are guaranteed that the complex scalar manifold that you have constructed this way, okay, admits a metric, a flat metric, okay, by Young's theorem. Yes.
Is J the first term class or the coefficient of J the first?
Coefficient of J. J is the Killer class. Right? So J describes the specific element of H11, right? Which is basically the Killer class of CPN. Okay, and then this whole thing is the first churn class. The J you think of as an element of H11 and you multiply by this coefficient. Right? So that's still an element of H11. Right? That's the first churn class. So what it is saying is that as long as we take this complete intersection in CPN, satisfying this condition, then you are guaranteed that you have a Calabi-Yau manifold. Okay, and then there are generalizations of this where you start with the product of CPNs, okay, and you can construct weighted projective spaces and so on. So there are various generalizations that one can consider, but this is the simplest class. Now I should add that having this manifold, okay, is far from saying what that Calabi. Some things have been done, but in general there is no known Ricci-flat metric that people have constructed. Okay. In particular, if you start from a metric on CPN, there is a natural metric on CPN, okay, which is called as Fubini study metric, okay, which is consistent of the Killer class, and if you pull it back on this manifold, you get a metric, but it's nowhere close to Ricci-flat metric. Is this point clear?
And so this is like finding a coordinate system in which that metric can be written as a Ricci-flat, but no one knows how to.
No, it's not finding a coordinate
Yeah,
system.
not
You really have to find a metric.
metric.
Yeah, because if it is Ricci-flat, then in any coordinate system it will remain Ricci-flat, right? So it's not that you have the metric and you are trying to change. It's that consistent with the topological conditions, right? So the Killer class should remain the same. You have to actually find a metric to do the job, okay, to be Ricci-flat. If you want to use it for string compactification.
So for instance, if you have a way of writing all the independent sections, the linearly independent sections of the tangent bundle,
Yes.
then you can actually use that to construct a VL bar at every point, which will be flat by just demanding that it's flat. I mean, suppose
Well, first of all, it's not. Of course, the Riemann tensor is not 0, right? Only Ricci tensor is 0. Okay. But effectively, what it amounts to solve is solving a differential equation, right? You know the metric is Killer, right? So basically, once this Killer potential is given, you know the metric, right? So you can set up a differential equation for the Killer potential, right, which is a Ricci-flatness condition. Okay. But of course, it's a partial differential equation, right? It's a function of many coordinates, and in general, solving that is hard. Okay, but the existence of the solution is guaranteed as long as the metric, as long as the manifold is has vanished in first term class. Okay. So this Young's theorem is basically a proof of existence of the solution to the differential equation, right? And in fact, it says that given the scalar class and the complex structure, okay, there is a unique solution. Okay, as long as the first rank class vanishes.
But here you considered a submanifold of CPN.
Yes.
But CPN by itself is a Calabi only.
No, it is not. Because CPN by itself would have this, right?
Oh, this is one. No,
Yeah, so the
this is
corresponding coefficient will be n plus 1. Right? So it's certainly not Calabi.
Also the first CP1 is basically a sphere
Exactly.
and that's not correct.
That's certainly not Calabi. Okay, so it turns out that even though you don't know the metric, lot can be done without knowing the metric. Okay, so now as you saw, okay, so this in fact also has another consequence, which is imagine that we have a Calabi manifold, okay, which means that it admits a Ricci flat metric, and you want to know what is the parameter, what is the family of such Ricci flat metrics you can put on the manifold. Okay, because any of them is a good choice, right? And those describe a kind of moduli space of vacuum, right? Because if there is a family of such metrics, each member of that family is a possible compactification, right? Which basically means that those should be considered as a moduli space of string vacuum. Okay. Now this theorem also tells you how to find that moduli space, at least locally, okay? Because it says that given a complex structure and a scalar class, okay, you can find a Ricci flat metric, unique Ricci flat metric. But if you change either the complex structure or the scalar class, then it will be another Ricci flat metric. Okay, because there are two metrics in different scalar classes, obviously are different metrics. Okay. So the moduli space of Ricci flat metric on a Calabi manifold are characterized by the complex structure and the scalar deformations. Okay, that because for every scalar class, okay, and every complex structure, you have a Ricci flat manifold. So as long as you know how to deform that, what is the whole space of complex structure and scalar forms, okay, you know what is the moduli space of matrix on Calabi manifold. Okay. Now for the scalar class, okay, we have already seen that locally at least the moduli are labeled by H11 parameters, okay, because that was the dimension of the scalar class. So now we want to know if a similar statement exists for complex structure moduli. Okay. Would it be expressed, the dimension of the complex structure moduli space, can it be written in terms of some Hodge number? Right? H11 was one of the Hodge numbers. Okay. And it turns out that indeed on a Calabi manifold we can do that. And this follows from two results which are not true. Okay, in fact, one result which are not true. There is a Calabi manifold, Calabi n-dimensional Calabi manifold, n complex dimensional. Calabi manifold. Has H n0 and H0n one dimensional. So Hn0 is n0 form, right? This means there is an n0 form which is Delbert closed, okay, and also del closed. Okay, if you can take the harmonic representative, it's Delbert closed and del closed. So there is a omega alpha 1 to alpha n dz alpha 1 to dz alpha n. Okay? So it's to begin with a function of z and z bar. But del bar omega equal to 0 basically means the del bar beta of omega alpha 1 to alpha n equal to 0. Right? Because all of these are alphas, homomorphic indices, right? There is nothing to anticipate, right? So you just get del bar beta of this equal to 0. Okay? So which means that omega is holomorphic. Omega alpha 1 to alpha n is holomorphic. And similarly, H0n means that there is an anti-holomorphic for omega bar alpha 1 bar to alpha n bar is anti-holomorphic. Now let's see how we can deform the how we can level the complex structure modular deformation. Complex structure deformation. So complex structure deformation. Okay, one way to do this is the following. Okay? So let's consider a dz alpha. Okay, holomorphic differential. Now you can think of this as a real form, right? After all, I mean it's a real manifold, right? You can think of it as a real manifold. So in that case, this is a real form. And now suppose we change the complex structure a little bit. Okay, deform the complex structure infinitesimally. In that case, what will happen is that this dz alpha, okay, regarded as a real form. Now we can again decompose into the holomorphic and anti-holomorphic differentials. But once, because you have deformed the complex structure, this is not going to be purely holomorphic. Right? That's the meaning of deforming the complex structure. So this then will go into A alpha beta, well let's call it dz alpha plus epsilon A alpha beta dz beta, which you don't care about, plus epsilon B alpha beta bar dz beta bar. These are really the parameters, the objects that is leveling the deformation of the complex structure. Okay? Now, it turns out, okay, again I will not try to prove this, is that if we consider omega alpha 1 to alpha n minus 1 d alpha beta bar dz alpha 1
Again. Oh, sorry.
alpha, yeah, because there is an alpha here, this is alpha
Okay,
minus 1.
minus 1.
The alpha n minus 1. Okay, given such a deformation b alpha beta bar, consider this object. It turns out that this is an element of H1 n minus 1. N minus 1 1. Which basically means that this is del bar closed. Okay, now in order that this is del bar closed, of course the B has to satisfy certain differential equations, but those come from integrability. Okay, which I have not shown. Okay. But what one can show is that this object is an element of Hn minus 1 1, okay, which means that the differential equations satisfied by B are such that this object is del bar closed. Okay. And the reverse is also true. given an element of h n minus 1 1, okay, we can reverse this to construct a deformation of the complex structure. Okay. So this then shows that the complex structure deformations are parameterized locally by elements of each one of h n minus 1 1. So which means that is h n minus 1 1 dimensional. But there is one difference from what we had earlier. For Keeler structure, we saw that it was h1 1 dimensional. But the Keeler mode deformations are actually h1 1 real dimensional. Okay, because we have a reality condition on the metric. Okay, you cannot take the metric and multiply by some arbitrary complex number and declare that as our new metric. Okay, so because the metric has to be real, okay, Keeler deformations are h1 1 dimensional, but those are all real parameters. But the complex structure deformations are complex parameters. Okay, because you can multiply this by some complex number, okay, and it still remains an allowed deformation. Okay. This asymmetry will be gone, okay, when you consider string theory, but just as a property of the manifold, okay, there is asymmetry that the number of Keeler deformations are h1 1 real dimensional, okay, whereas the number of complex structure deformations are h n minus 1 1 complex dimensional. Is this okay? Okay, so lot of our
Sorry,
yes.
if one is to follow this logic, suppose one is not termed linear in B but quadratic in B, then one will also tend to conclude that in minus 2 comma 2 would be the element. Is it ruled out because we are looking at only infinitesimal linear?
Yeah, we're considering only infinitesimal deformations. Yeah, exactly. Because you want to count the dimension, right? For counting dimension is just linear deformations are enough.
So those would exactly. So those would not be relevant. Because
Exactly. Yeah. But the point is, of course, that one has to make sure that this. First of all, B has to satisfy certain differential equations, right? And then there is an integrability condition. Right? For Calabi-Yau manifold, things turn out to be simple, right? And one can, so that as long as this object is harmonic, for example, right? This describes an allowed deformation of the complex structure. But you are always considering the infinitesimal deformation because you want to count the dimension of the moduli space.
so this omega is it globally proportional to the epsilon tensor for the holomorphic or
Yes,
is it globally proportional to epsilon?
it's proportional to epsilon tensor, but the overall multiplicative
It doesn't
factor
depend on Z.
always depend on Z, exactly. Because I mean, it has to be the case, right? Otherwise, what else can it be?
What else can it
Right?
be?
Yeah, we're totally antisymmetric in all the holomorphic
That's
cases. Yes.
When you say that the Keeler deformations are h n minus 1
H1.
real dimensional,
Keeler deformations are h1 1 real
and
dimensional.
complex are same thing but complex dimension.
Not same thing. It's h n minus 1 1.
Okay, fine.
Right? h n minus 1 1 complex dimensional. Okay. So for n equal to 2, they are the same things, right? But otherwise, they are different.
So when they're saying that means that for a given Keeler this thing we can multiply the there's still some real dimensions left over here, right? As in when you write the complex dimension as real numbers,
Yes.
so that means there is some freedom allowed here which is not there.
Yeah, because you can choose these to be complex. Right? This B alpha beta can be arbitrary complex numbers. Okay, so when you solve this differential equation, right, you find a solution to differential equation. So you might take a harmonic, and then you can take arbitrary complex linear combinations of these, right, and those will give a valid allowed complex structure deformation. Okay. So this basically, so when you say you take go in the reverse, right, that take an element of Hn minus 1 1 and construct B alpha beta bar from there. Okay, that you can do by reversing this. Okay. But now the question is, so that gives an element, and now can you take arbitrary linear complex linear combination or arbitrary real linear combination, right? Here you can take arbitrary complex linear combination, because multiplying this by arbitrary complex number still gives valid complex structure deformation, which is not the case for a metric. But as I said, this asymmetry will go away in string theory because string theory contains other fields. Okay. In particular, it has this two-form field from the NS sector, okay, which will also have H11 complex, H11 real deformation parameters, okay, and they will combine natural into a complex combination. Okay, but just as a metric, as a geometry of the Calabi-Yau manifold, okay, the scalar moduli space is H11 real dimensional, complex structure moduli space is Hn minus 1 1 complex dimensional. Okay, so Calabi-Yau threefold means 3 complex dimensions. So in this case, okay, most of the Haas numbers are fixed. So first of all, H30 and H03 are 1. Here the holomorphic 3 forms are anti-holomorphic 3 forms. H00 is always 1 as long as the manifold is connected, and also is H33. One. It turns out that on Calabi-Yau manifold H10 is 0, and so is H01. And so is H02 and H20. And then there is a duality which is HPQ is H, in fact HQP of course because of the complex conjugation, but there is also Hn minus P, N minus Q, this is the Hodge duality. So using this we can also set many of the other things to 0. So in particular H23 equal to 0, H32 equal to 0, H13 equal to 0, H31 equal to 0. So basically, only 2 unknown numbers remain. So H11, which is also the same as H22. One of this pointed reality. This is unknown. Okay. This is unknown in the sense that it can be defined on different Calabi-Yau manifolds. And H12, which is the same as H21, this is also unknown. Okay. So given a Calabi-Yau manifold, okay, Calabi-Yau threefold, which is of most interest to us. Okay. If you want to know what are the numbers that we really need, okay, what are the most important numbers that you want to calculate? It's these two, H11 and H1. And as we saw, these are also the number of Taylor deformations and number of complex structure deformations. Are there any questions? Okay, so now we will discuss another important property of Calabi-Yau manifolds, and this has to do with the spinors on Calabi-Yau manifold. Okay. So let me remind you again how spinors are defined in general on a compact manifold, say, okay, like Calabi-Yau euclidean manifold. So first we look at the tangent space group. Okay, so take Calabi-Yau 3, 4. So the tangent space is SO6, has tangent space group is SO6, right? Which basically means that the general holonomic group of the manifold will be SO6. Okay, any real manifold. Okay. Calabi-Yau are special because on Calabi-Yau the holonomic group is SO3, okay, which is a subgroup of SO6. But in general, any 6-dimensional manifold will have a holonomic group of SO6. Now, vectors and tensors transform under appropriate representation of SO6. Right? Vectors and tensors you can always convert using the Feuerbach, so you can convert all the curved indices into flat indices. Okay. So, for example, in vector field on this compact space, on a 6-dimensional space, will transform in the 6 representation of SO6. Okay. A tensor field, a symmetric tensor, okay, will transform in the symmetric and antisymmetric symmetric part of 6. So that's what, 6 times 5, 6 times 7 by 2. Okay. This is 21, okay. But this you can decompose into 20 plus 1. 1 is the scalar and 20 is the 20 representation of SO6. Okay, so this is how you can figure out how the various tensors transform. Okay. And you can write down covariant derivatives, okay, using the spin connection. Now spinors also transform under certain representation of SO6, but these are spinor representations. Okay. So a basic spinor on a 6-dimensional manifold will transform in the 4 representation of SO6. Okay, the spinor representation of SO6 is 4-dimensional, okay, which in fact is very easy to see because SO6, at least as an algebra, is isomorphic to SU4. Okay, and SU4 certainly has a 4-dimensional representation, right? That's the spinor representation of SO6. So now, if we want to write down the covariant derivative, d mu of chi, suppose this is the any representation. So this will be given by del mu chi plus sigma omega mu kg sigma v on chi. Well, this is the spin connection. Let me write not del mu but del m because this is internal indices. So these are spin connection. This is a generator in the given representation. Okay?
GA, right?
Pardon?
GA, B was also be A.
Yes, DM. So now let's imagine that we have some fixed point on the manifold, and we take a field in any representation and parallel transport it and come back to the original point. Okay? And you want to know how does the field, to begin with, suppose you start with chi and you end with chi, how are these two related? Okay? And the answer in fact is very simple. This is given by R of HC. I'll explain what this is on chi. What is HC? So this is an element of SO6 describing holonomy around C. So if you are a vector field, okay, then vectors would come back by multiplied by this H of C. This is an element of SO6 group. R means simply that it's the representation of that particular group element in the representation into which chi belongs. Holonomy is a general concept. Okay, it's an element of the group by which you transform the fields. Right? If you change the representation of the field, okay, all that happens is that instead of using the original group element H of C, you have to use the corresponding representation in which you have taken the field. Is this clear? Right? Because holonomy is a general property, it doesn't care about what representation it is as long as you use that particular representation to compute the matrix. Okay, now we know that on Calabi-Yau, okay, with Ricci flat metric, H of C belongs to an SU3 subgroup of SO6. Right? Calabi-Yau manifolds have SU3 holonomy. Okay, or Calabi-Yau manifolds with Ricci flat metric have SU3 holonomy. So H of C has SU3 holonomy. So what you are looking for is a representation of SO6, but the SO6 group element belongs to an SU3 subgroup. Is this clear? Okay. And that SU3, how it's embedded in SO6 is easiest to see by representing SO6 as SU4. Because if you think of this SU4 matrix, suppose you are using the Skinner representation, right? So it will be a 4 by 4 dimensional matrix. So SU3, the holonomy group, basically sits here. And then this is 0, 0, 1. This is the representation matrix that we will get. Okay. If your holonomy is SU3 holonomy. Okay, this is the way SU3 is embedded in SU4. Now this means that if we start, suppose the starting chi is along the fourth direction. Then R of chi, if chi is this, then R of HC on chi is the same. Because SU3 matrix is here, right? It doesn't act on the last component. Okay. Which means that take any closed curve through P, chi will always come back to the original point, original value, as you go around the closed curve. Okay?
But if chi have this particular,
If you take chi, if you take the initial chi to be of this form, okay? If any of the other three components are non-zero, then it will transform. Okay, so only if you take initial chi to be of this form, then this property is true. This also means that if we take the initial chi to be of this form, okay, and parallel transport it from P to another point Q, then the result doesn't depend on which path you have taken from P to Q. Okay? That's the same statement that when you go around a closed curve, chi comes back to the original value. Right? It means that when you go from here to here or go from here to here, chi is the same. Okay? So this means that starting from this, okay, imagine that at P we have declared that chi takes this value. Okay? We can now define chi everywhere on the manifold by parallel transport. Okay? And that definition is well defined because that definition doesn't depend on the path along which you are parallel transported. See? Normally you cannot do this, right? Normally you cannot start with a vector field here, and define it everywhere by parallel transport, right? Because whether you go around this curve or this curve will make a difference. Okay? But in this case, if we take chi to be of this form, then it doesn't make a difference.
That means this covariant derivative is 0.
Exactly. That means that now this defines a field, okay, because chi is now defined everywhere on the manifold. Okay, so it's now a spinor field, not just a spinor at a given point. Okay, and that spinor field has vanishing covariant derivative. Okay, so Calabi-Yau manifold admits a covariantly constant spinor. This is 3-dimensional. In fact, this is true for all Calabi-Yau manifolds. So this is covariantly constant spinor.
But is this not particular that at some point one has to start with this form of chi?
Yes. So which means that it admits one covariantly constant spinor, not many. Okay? You start with this chi, okay, and you will get a covariantly constant spinor. So on a given Calabi-Yau, there is a single covariantly constant spinor.
This is true for all Calabi-Yau manifolds or just Calabi-Yau 3-fold?
Calabi-Yau 3-folds, all Calabi-Yau manifolds have covariantly constant spinors, but the number changes.
Here it so happens that algebra of SO6 is same as that of SU4, so we do
Yes.
we do this. Now for a general twin-dimensional this thing, such things will not happen, right?
Yeah, but you don't need it. What you need is that you take SO6, right? Spinors belong to certain representation of SO6. Right? Now, holonomy is a subgroup of SO6.
Yes.
Right? You have to ask that under that subgroup, how does the spinor representation decomposes? That's a perfect well-defined question for irrespective of whether G has a specific representation or not, right?
Yes.
So suppose the holonomy is H. Suppose the full tangent space group is G and the holonomy is H. Okay? You have to ask how does the spinor of G transform under H? Okay? If it has a singlet, then you can do this. Okay? Because if there is a component which is singlet under H,
Like this one.
yeah, that means that doesn't get transformed under H, right? And hence, for that component, starting from a spinor with but only that component is non-zero, you can carry out this procedure.
But then here only one component was left. For higher dimensional Calabi-Yau, it can be more than one, or it will be only one.
Well, for K3, for example, right? For K3, what happens is that if I have SU, so SO4, there again SO4 is SU2 times SU2. And the spinor representation basically goes as 2, 1 plus 1, 2. Okay. Holonomy is in SU2, one of the SU2s. Okay. Which means that half of the, so these components are neutral. Suppose the holonomy is in this. Okay. Then this component is neutral because this is 1 unlike this, right? So for these components, you can start with any of these components and then parallel transport and get what you want.
So there, in this case, there are two distinct spinors there.
There will be 2, yes. I mean, if you take a 4 complex dimensional spinor, right, then 2 of them will be unchanged. Okay, depends on what you start with, right? What is the representation you start with. If you start with this representation, then nothing will be left. Right? So the spinor representation here is irreducible, right? So you can either take a chiral spinor or an anti-chiral spinor. Okay? If you take a chiral spinor like 1, 2, right, then it's of course not neutral. And this you can do for every SUN in general, right? You take SO2N, right, a spinor of SO2N, and then you can ask how does it transform under SUN? Does it have a singlet? As long as it has a singlet, it can be used to construct a covalent constant spinor.
So in this case, can it have more than one covalently constant spinor? You can have,
No, in this case you cannot have more than one.
but in SU3, if you have trivial curves which say you can contract.
Yes. So if the holonomy is a subgroup of SU3, then you can have. But if the holonomy is the whole group SU3, right? Then see, it has to take some value at P, right?
No, suppose it comes back to the identity of SU3 somehow. The holonomy comes back.
Yeah, that means if it all curves, it comes back to identity of SU3. That means the holonomic group is trivial. Okay. So when you say that it has SU3 holonomy, right, it could be that it has no holonomy. Torus, for example. T6 is also an example of a Calabi-Yau manifold, okay, where you can certainly have more. Right?
There are certain curves which will give identity, but not all the curves.
Exactly. But the point is for this to hold, you have to make sure that on all curves it gives identity. Right? Because otherwise there will be some obstruction in extending this to other points. So the existence of these covalently constant spinors basically tells us that Calabi-Yau, when you compactify on Calabi-Yau manifolds, okay, you have unbroken space-time supersymmetry. Okay, so let's see how that happens. Again, let's take Calabi-Yau 3-fold, but you can repeat the analysis for Calabi-Yau 2-fold, in particular K3 for example, or K3 times T2, which is also a 6-dimensional space. Okay. So, suppose you take a 10-dimensional wire on a wire spinor. These are the basic objects which generate supersymmetric transformation, right? Okay. So, for heterotic, you only have one such spinor. For type 2, you have two such spinors, right? One for type 2, one is left-handed, other one is right-handed. For type 2, we both are have one parallel. Okay. But let's take one of them. Now, your manifold that you are taking is Calabi-Yau 3-fold times R31. Okay, this is the 3 plus 1 times the Minkowski space. Okay, so the tangent space group here is SO6, which of course becomes part of SU3. Okay, the actual holonomic group becomes SU3. Okay. And R31 has SO31 as the tangent space group. Now, you can ask how does the 16, okay, this is 10-dimensional Mayanov spinor, how does it decompose under this subgroup of SO? So this is transform under SO9, 1, right? Transform under SO9, 1. Okay. But SO9, 1 has a subgroup which is SO6 times SO3, 1. Okay, the product of two tangents. Okay, and that's a relevant question, that how does this 10-dimensional spinor 16 transform under this, and it turns out that it transforms as 4 of SO6 times left-handed y of SO31 plus 4 bar of SO6 and right-handed y Now, if you take 16 bar, which is the other chirality, basically what happens is this 4 gets replaced by 4 bar and this 4 bar gets replaced by 4. Okay, the correlation gets changed, but that will not really matter for what we are going to discuss. So now we can ask that you remember that for unbroken supersymmetry, we need covariantly constant spinors. Right? That was the condition. That unbroken supersymmetry requires that d mu of epsilon, unbroken supersymmetry, unbroken SUSY, required that dm on epsilon is 0 and also d mu on epsilon is 0. Because all covariant derivatives are defined, right? Okay, this was the condition that the variation of the gravity law is 0. Okay, if there are other background fields present, then of course the conditions are more complicated. Okay, now this is trivially satisfied because you are considering flat 4-dimensional space. If you take epsilon to be constant, independent of the 4-dimensional space time, then this is automatically satisfied. Okay, so take epsilon to be independent of R31, so basically constant. So this is automatically satisfied. So we will have to solve for this. And we know already how many solutions are there. Right? Because from this 4 of SO6 we get one component. Right? Because one out of these 4 components, there is a unique covariantly constant spinor that you can construct this way from 4. So you get one component from here, so there is a left-handed file of SO31 and then right-handed file of SO31. Because 4 bar will also have the same property. Right? 4 bar also have a singlet. So together we basically get a pair of complex conjugate spinors. Okay, these are just complex conjugates of each other because if the original one was Majorana, right, then these are just complex conjugates of each other. Okay, so basically the number of unbroken supersymmetries that is left is corresponds to one Weil spinor of in 4 dimension and its complex conjugate. So this gives you one Weil spinor in 3 plus 1d plus its complex conjugate. Which basically means n equal to 1 supersymmetry.
DM doesn't have Christoffel symbol terms?
This one?
Yeah.
Yes, it does. But we constructed a solution to dm epsilon equal to by this procedure, right? It has Christoffel symbol terms, right, or spin connection terms, right? But precisely this construction guaranteed that at least for this starting point, you can solve for dm equal to 0. So this is 0 not trivially, not because epsilon doesn't depend on the internal dimension, it does depend on the internal dimension. Right? But this is 0 because you can solve this analysis and holonomic being SU3 so that it is possible to find a solution to dm epsilon equal to 0.
But if you switch on different other fields, those will also come in.
Yes, so if you switch on other fields, then of course you have to reanalyze it. Right? Reanalyze the effect of supersymmetry. Right now you are assuming that only the metric background is present, nothing else is switched on. Is this okay? So this shows that heterotic string theory compactified on a Calabi-Yau 3-fold times R31 basically has n equal to 1 supersymmetry. In 3 plus 1 dimension, it will give an effective theory n equal to 1 supersymmetry. If you take type 2, you start with 2 of these. Okay, each of these give 4 supersymmetries. Okay, and n equal to 1 supersymmetry. So together they correspond to n equal to 2 supersymmetric theory in 4 dimension. Okay, so this is straightforward. So heterotic and type 1 compactive on Calabi-Yau 3-fold will generate n equal to 1 supersymmetry. type 2 string theories, compactive and Calabi-Yau threefold will generate n equal to 2 supersymmetry. K3 times T2, okay, also you can analyze this way. K3 times T2 is again a 4-dimensional manifold. Okay. But from this analysis what we showed, okay, is that basically K3 will break if you start with certain number of components, 4 components, it will keep 2 of the 4 components. Right? For every 4 components you actually get 2 unbroken supersymmetries. Okay. So to begin with, if you start with 16 components period, okay, that's another way of doing the counting. Okay, see here instead of doing the counting this way, we can say out of every 4 component you get 1 which is unbroken. Okay, so 16 by 4 is 4, right? That's another way of counting n equal to 1 supersymmetry. So heterotic, so if you take K3 times T2, right? T2 of course has trivial polynomial, okay? And in K3, out of a 4 component spinner you get half of it left over. Half of it can be made covariantly constant. Okay. So half the supersymmetries are preserved, half are broken. Okay. So from 16 you can get 8 unbroken supercharges which corresponds to n equal to 2 supersymmetry in 4 dimensions. So heterotic on or type 1 on K3 times T2 will give you n equal to 2 supersymmetric theories, whereas type 2 string theory on n equal to on K3 times T2 will correspond to n equal to 4 supersymmetry in 4 dimensions. Okay, so maybe I'll stop here and then we'll continue. So tomorrow we'll start discussing actual compactification and Calabi-Yau manifolds.
So type 2 on K3 cross T2 is n equal to 4.
Is n equal to 4.
How many dimensions is K3?
K3 is 4 dimensions, 4 real dimensions, so 2 complex dimensions. Okay, that's why we are taking K3 times T2. So K3, I should say that in Calabi-Yau one-fold, which is 2-dimensional Calabi-Yau manifolds, are unique. Only T2 is the only possibility. Calabi-Yau two folds, right? 4-dimensional Calabi-Yau manifold. Okay. You have T4, that's one possibility, or K3. Okay, you can, so there's no other 4-dimensional Calabi-Yau manifolds. Okay. But once you go to 6 dimension, okay, there are many. Okay, in fact, initially when people started working on this, they thought there are only a few, but now you know that you can construct huge classes of Calabi-Yau manifolds, which are 6 dimensional.
In general, direct products of Calabi-Yau manifold will also be a Calabi-Yau manifold, right?
Yes, yeah, but they will have reduced holonomy, right? Let's say K3 times T2 is a 6-dimensional Calabi-Yau manifold, right? But its holonomy is SU2 instead of SU3, right? Which is also a Calabi-Yau because SU2 is a subgroup of SU3.
But it's smaller than.
Exactly. So when you normally talk about Calabi-Yau n-fold, right? You think of Calabi-Yau manifolds whose holonomy is actually SUN, not a subgroup of SUN.
So having a subgroup will give you more supersymmetry.
Yes. So if it's in a subgroup, it will typically give you more supersymmetry.
Yeah, you discussed that in Calabi-Yau n-fold we have Hn0 and H0n is one dimensional.
That's right. Yes.
So wouldn't just the existence of these one dimensional imply that the manifold is Ricci flat? Because if I have an n-fold, I have an Hn0, I have an n form, I take a norm of it, I'll just say the volume form. So basically the norm would be proportional to the root g.
Root g, yes. But
Right. So I can write R mu in terms of del bar log of root g.
yeah, I don't think you can. Okay, there may be a relationship between the n0 forms on a metric, but then you have to ask how to construct the n0 form, right? I mean, in fact, I don't know whether the relationship is so straightforward because it's not guaranteed. You see, you can construct some metric, okay? But what you have to make sure is that metric is a Ricci flat metric. You see, n0 form, the existence of an n0 form, right? It's a holomorphic n0 form, right? So that by itself doesn't care about the metric, right? To construct a holomorphic n0 form, you don't need the metric. Now, given that structure, okay, you have lots of possible metrics, right? There is a unique metric for a given Kerr class. Right? Even when you know the n0 form exists, right? There are lots of possible metrics. Only one of them is Ricci flat. Right? So I don't think you can directly go from the holomorphic form to the construction of the metric. Right? The holomorphic form in principle could be constructed without knowing about the metric. So, if you want to know whether you can construct one metric, yes, you can probably use a holomorphic form to construct a metric. Okay? But it's another thing to claim that that metric is Ricci flat.
So, but then because root G will be proportional to the norm of the sigma that you wrote.
Okay.
So
Suppose you take root
it's
G
a
to-
constant at the end. When I take del bar log of that, I get a 0.
But del bar log of root G being 0 is not a Ricci flatness condition, right?
There's a metric.
Yeah, we can check this, but I don't think that there is a simple construction from the holomorphic form to the metric for the Calabi-Yau manifold. Because the holomorphic form people have constructed on a Calabi-Yau manifold, right? But not the metric.